This lecture is going to cover three different topics. We're going to quickly go over what quasi-experimental design is, then we will spend a little bit more time going over item response theory, and then at the end we will wrap up with a little bit of walking through a correlation table and how we interpret what's happening in a correlation table. So starting with quasi-experimental design, when we are doing research, we normally have an experimental condition, maybe several if we're testing different modifications, and a control condition where they're not getting any of the experimental modifications. In education, we are most often doing this with curriculum or behavior interventions. So our control group would be the students who are getting whatever currently exists, or if there isn't anything that exists, they are just doing as normal. And our experimental condition would be getting the new intervention, and we essentially compare between the control and the experimental condition to evaluate how well that intervention works. When it comes to doing research in schools, we rarely, if ever, can actually do a true random assignment to our experimental conditions because we can't just mix students up into new classrooms. They're in the classes that they are. No school administration is going to let us just go in and scramble everybody up. So we have human factors that are just going on that are going to directly impact our study, sometimes in strong and sometimes not so strong ways. So we can't do a true experimental design because we can't do true random assignment. So experimental research in education is often quasi-experimental or quasi-experimental, depends on who you are, how you pronounce it, because we can't do that random selection. It's still experimental because we will have a control group and an experimental group, but the control and experimental group aren't randomly assigned. They are kind of based on our options that we have, where one class might be our control and the other is the experimental, however we're separating it. In order to account for all of those human factors that can affect our study, we try to collect as many of those descriptor variables as we can and try to match them often between our experimental group and our control group. There are things we can do to help us get that enough information to be able to match, and that is having large sample sizes. The more people you have, as widespread as you can get, the better chances you have to be able to match control and experimental participants with similar demographic descriptor variables. So we're at least keeping those the same. Obviously, we can't keep everything the same because they're in different classrooms, they're from different families, they're experiencing different things, potentially different schools depending on how you're doing your study. So we can't control everything, but we try to match as much as we can in terms of characteristics so that the thing that is changing for the most part is if you're in the control versus experimental condition. We will usually see this in studies that are doing a quasi-experimental design. They will tell us what the demographics look like for their control and experimental groups. If they've done pre-tests or anything like that to get a baseline, they'll also tell us that information. And if in the event those things are significantly different, they will let us know, and it should affect how they interpret their results as well. So it's things that not only the researchers are thinking about, but we should think about as readers as well when we're interpreting their work. So that in a nutshell is quasi-experimental design. As we get further into the semester, we'll get into other ways that we design education research, but this is an overarching methodology of approaching experimental research in education. Now going on to item response theory, or IRT, often you will see it abbreviated a lot. This is a methodological framework that essentially helps us approach how our assessment is working, particularly at the item level. So how difficult or hard and how discriminatory an item is. I'm going to define that right now because it is not how racist or sexist or homophobic your item is. Discriminatory in item response theory means how well the item can distinguish test takers by skill level. So the thing it is discriminating on is ability, and not in a biased way, but in being able to sort high, medium, and low skill levels on a particular item. We're looking at this for an item by item level. So if your item has low discrimination, it would mean that getting the item right or wrong isn't a factor of your skill. So it's easy to guess the right answer potentially, or just randomly picking an answer lets you pick the right answer, whatever is going on. Um, it's not separating students who have high skill level, high content knowledge, whatever it is that you're measuring, from students who don't have high levels in that. And ideally, we want an item that can do that because we're trying to assess our students. And so if our question is super easy and everybody is getting it right, we're not really getting a lot of information on how well our students are doing skill or content knowledge wise. The other thing we want to look at, which is related to discrimination, is how difficult the item is. Because how difficult it is will impact how discriminatory it is. It isn't necessarily a one-to-one because sometimes the item's difficulty is not because of a skill level thing, it is because the item is written poorly and there's another probably skill that the students need to interpret that item. Often it is reading comprehension, because if your item is super hard to read, your students are spending time deciphering your question, not actually doing the math skill that you want them to do. So you're actually testing reading comprehension, not math. So we want to look at the difficulty of the item and the discriminatory power of the item, because those two pieces of information can also tell us if there's something going on in terms of how the item is designed. But in general, if your item isn't difficult, everybody's going to get it right regardless of skill level. Now, when we're thinking about teaching broadly, there are probably questions that you do want all of your students to get right because it is basic knowledge that they need to get, like, they need as a foundation in order to progress to other things. So this is not thinking about it in a summative or formative assessment way. We're thinking about this in a psychometric way, which is the principle of psychological measurement. So we're thinking about, we want to actually know who is getting right, this question right or wrong is based on skill and not other factors. So if your item isn't difficult, everybody's going to get it right. If your item is super difficult, barely anybody is going to get it right, and so it might only discriminate at really high skill levels. So it depends on what you're looking for, and you might want a range of items where some have low discriminatory power, some have high discriminatory power, and some are kind of in the middle, because that lets you distinguish fine changes in skill level at the low end, at the medium area, and at the high end too. So it's not necessarily that you want a very discriminatory or a very not discriminatory item, or a very difficult item or a super easy item. A lot of it comes down to, you want a little bit of variation in these things so that you're able to capture all of your spectrum of students and capture the changes, subtle changes in skill level across the whole spectrum of student skills. Now, a note before I get to the next slide that's going to have a graph on it. Ability level in IRT is a standardized scale. So average skill is set as 0, and then it usually ranges from -4 to 0.4. It kind of depends on what scale the researchers are using. Sometimes it can be 0.3, or not 0.3, it can be 3 to -3. Depends on what range they're using, but it's always going to be standardized, where 0 is average. So 0 is not no skill, 0 is average. So speaking of this, we're going to work through this item characteristic curve. This is what a IRT model would let you know or output based on you getting information from your students on a series of items. So each of the lines on this graph is an item. They've color-coded 2 here, and I'm going to talk about those in terms of what they're doing. But each of these lines is an item. So this could be an item characteristic curve of a quiz, potentially. So most item curves are going to be logistic or S-shaped curves. So we start kind of flat at the bottom, we curve sharply, and then we start plateauing again. Now you might notice there's different looking lines here, where this one doesn't have a flat at the bottom, and the red one does, but it doesn't really have a flat at the top. These are factors of the difficulty of the item. So in a nutshell, we can determine difficulty based on where the line starts at the lowest skill level, where if it is down here at the bottom, it's pretty difficult. There is basically zero chance that if you have low mathematical ability that you'll get item 5 or question 5 right. However, if you're answering blue question 8, it's not a super high chance, maybe like 15 or 20%. We're looking at probability here, so 0.5 would be 50%, 1 would be 100. You have like about a 20-ish% chance of getting item 8 right, if you're on this low end. Conversely, we can look at it and see on the high end, or rather when this curve starts changing to where you get over 50% probability of getting it right. For the red item, question 5, that's not happening until you get almost to skill level 2. So it's a fairly difficult item. You need to be above average already just to have a 50% chance of getting it right. However, if we look at the blue line, that crossing of 0.5 happens before you get to -2. So you can have moderately low ability in math and still get this item right 50% of the time. So we can look at these to see where difficulty is based on where we're crossing that halfway point in our lines. And we have, across all of these questions, a lot of variation, which is going to be good to capture different ability levels across the span. However, it's not really super capturing the high end because our last question is just right about above average, I would say. The other thing we want to look at, which I've done these out of order, but the slope will tell us how discriminatory the item is. So how these, in general, these questions have almost the same slope. In a sense, the line keeps moving up at a particular slope, depending on both the difficulty and sometimes it can be a separate factor from difficulty. The area this slope crosses, or this line will cross, is based on that slope. The larger amount of distance it can cross on our x-axis, the more discriminatory it is. And so I would say out of all of these questions, the item that has perhaps the best discrimination would probably be this kind of middle line here. And that's mainly because we are spanning all the way from maybe like -3 up to about 1. It's not the best. If I wanted an item that was really discriminatory, what I would want is something perhaps going across to there where it doesn't approach 100%, you're going to get this right too quickly, but it also isn't riding along 0 and then suddenly going up. Now, not every question looks ideally like this kind of nice long line here, but in general, the slope is going to help us discriminate if you are a -1 for that question. You have, actually, let's use the red line. So say if you have -1 math ability, you're just a little bit under average, you have a pretty small chance of getting the red question 5 right. However, once you go to about 1, your probability of getting that right, it's not at 0.5 yet, but it has increased by quite a lot because we've gone from down here all the way to up here. So this item is fairly discriminatory, particularly for students at about the -1 up to 4, because we're not even approaching 1 at that point. Conversely, I'd say the blue question is more discriminatory for students with lower ability, so we're seeing that slope begin at -4, and it keeps going, but it starts petering out about at average. So it's going to be able to distinguish students on the lower end of the mathematical ability, but it's not distinguishing them once they're at least average or above. I'm going to click through these a little bit. Okay, and that was and so I've written some summaries there, basically of what I have just gone over for the blue line and the red line. So in general, and I mentioned this at the beginning, we want an assessment to have different curves. We don't want them to be all the same unless we can get something that looks like the purple line that I drew. More often than not, we're not going to have that though, so it helps to have multiple items with different difficulties and different discriminatory capabilities, so that when we average all of these, because that's what's going to happen when you look at the score, for any given student, we are covering our full spectrum in terms of being able to discriminate between high-level learners and low-level learners and average learners. So item response theory focuses on what the item properties are, but in the grand scheme of things, we are thinking about those item properties in a pool of items that is the assessment. So we wouldn't want to just look at one item and call it good. We want to look at what all of the items are doing and make sure that our assessment has items that are able to help us capture different portions of the mathematical ability spectrum. So how do we get this information from an article that is using item response theory, particularly when they are designing their own assessments? We may not see this if they're using a pre-established assessment. If they are using a pre-established assessment, they will be referring to it, and you can go find that information probably in whatever citation they give you. But for some studies, we're going to look at studies that have made their own assessments, and they should be giving us this kind of information. Not all assessments are going to do that. This is in particular for assessments that are measuring skill of some capacity. So if we were doing this as researchers, how do we generate this data to show that our assessment is working well? First, we want to test our measure with a lot of participants and look at their data. So you might guess, this is a part of the validity and reliability process. You can get this information. We also want to use a separate measure that is already valid and reliable so that we can have a proxy of skill level to compare our assessment to. From my understanding, you can't do item response theory with no other indicator of skill. You need to have something that you're referencing that you know is a good indicator of skill level to see how your item is distinguishing amongst your participants or discriminating. So for the case of the reading that we did, the Does Homework Design Matter? The Role of Homework's Purpose in Student Mathematics Achievement, they designed their own measure to look at students' skills in a particular area of math when they were testing out different, the effects of different homework kinds on students' achievement. The metric that they used to help validate their measure was students' previous grade end of year scores. So that was their ability level they used to then test how their items were working across students of different abilities. Is that the best measure of ability? Maybe not. I don't know. It kind of depends on what they're doing and if there are other things they can use that are potentially more valid and reliable. I would assume that the end of year scores are a fairly reliable assessment, but there might be some other instances in different areas of study where there is a really good assessment for that skill. You would want to use that. You want to use the best indicator you can find. And so that's what these researchers chose, was their end of year scores. So when we're thinking about that article, what was all the other stat stuff that they gave us? There was a bunch of tables in the article, and we're going to go look at those tables. There's a lot of numbers, but we'll walk through them. But first, before I do that, I want to tell you why that they gave us all that information. And that was so we could understand their item response theory results for each of their items. With that information, we could generally create those item response theory lines if we wanted to. The difficulty and the slope in particular were really important values in the table that they gave us, because the difficulty is telling us where that S-curve is intersecting with that y-axis, and if there is a flat part to that at the low end level or not. And then the slope is telling us how fast that line is going up to when it starts plateauing at the higher ends. So how discriminatory the item is related to the slope that they give us. Another thing they gave us was an eigenvalue. And so an eigenvalue is a term that is used when we are doing a factor analysis. We're going to talk about factor analysis in more detail later as its own separate lecture because we're going to encounter that as well in education research. But in general, it is a way of measuring how a person's responses group together across items or not. It depends on what you're doing. In a nutshell, you have a construct that you're trying to measure. If your measure is capturing that one construct, the person's items are going to group together across the whole measure. If there is another construct in there, so say we have two constructs, I would suspect that some items correspond more closely to one construct and some items correspond to another construct. So they gave us the eigenvalues to show that their measure is a single construct measure. It is just getting this one particular aspect of math skill that they were trying to assess in their measure. So the eigenvalue was for them to show that their measure was designed well and wasn't capturing some other skill. With IRT, there is an assumption that your measure is unidimensional. That means it's only measuring one thing, or one construct. And like I said, they use a factor analysis to figure this out, where the construct should be a factor. And if you see there's more than one factor, then you need to evaluate what kind of framework you're using to demonstrate the effectiveness of your measure, or you need to redesign your measure to make it one factor. One of the two options. So given they were using IRT, they needed to make sure their measure only had one factor. All right, so let's go through this table that I just mentioned I got all this information from. And we're just going to go from left to right and interpret what is happening on each of these columns. So first, we have each item. This was a 10-item assessment that they gave us, or that they developed. They give us the mean score. This is what the students are scoring. My guess would be it is either correct or incorrect, so your score is either 0 or 1. And so the average is not exactly super useful in terms of telling us how many people were getting it correct or not, but it does tell us in a way how, I guess, the students skew towards getting it more correct. Like in the case of 0.87, they're closer to 1. But in the case of 0.33, a lot of students aren't getting that question right. We do have standard deviation, which tells us a little bit about the range of students' responses, which we could, if we wanted to, essentially you can add and subtract this number to know where the majority of students are getting in terms of scores. It's a little harder to interpret given right now we're using a 0 to 1, they either got the answer correct or they didn't get it. Now alpha, we haven't really talked about too much yet. We are going to talk about later because it does come up a lot in assessment design. This is essentially how reliable the item is. Now, when they're doing this per item, here it is, I would say, less of a useful measure for us, in part because when we are looking for reliability of measures, I don't exactly know how they have measured this alpha for these items and if they're comparing it to anything else to establish the alpha. But in general, when we see people using an alpha, we want to look for a reliability that is at least 0.7, ideally higher than that, but 0.7 is kind of an acceptable minimum. And that just means the item is producing consistently the same kind of data. Sometimes that might be because we did test retest. It might be looking at this across different versions of the assessment, or we might be correlating with some other factor. In this case, they're all above 7, so I'm not worried about the alpha. Now we get into the slope, which is one of our big indicators of how these items are working with students. So the bigger the number, the steeper the slope it is. Now, if the slope is super steep, it is quite discriminatory, but it decreases the range across which it is discriminatory, because if the slope is super steep, we are getting up to our plateau much quicker. And I'm actually going to draw this. So we're going to do some guesses with some of these numbers. So I'm going to start off with that 0.21. So let's draw us a nice little graph here. I'm not going to label it by anything, but if I have a slope that is 0.2, it's going to be pretty steep. That slope really, it goes up pretty fast. And so we're barely halfway through the graph before I've hit my skewed plateau there. Now that next one underneath, let's go green, that 0.18, it's still pretty high, but it's not as high. So I might be sloping about that. And then I eventually get to my plateau somewhere over there. It's hard to draw with a mouse. Then we can compare that to this 0.9 here, where it's not even 1. So I would say that slope probably looks something like that. Maybe this item is super easy to begin with, so I didn't really account for where my intersection is on difficulty. I wasn't matching that here. This is just for looking at slope values. So that is all this graph is the slope. So we're seeing a bunch of different slopes here. We have some that are super steep, some that are not so steep. So this is telling me essentially how much distance this item is covering in terms of discrimination. Discrimination is essentially a factor of both slope and difficulty, so we also want to look at difficulty as well. Now, difficulty can have various different intersections, essentially where the line will start to curve up. The lower the value, the less discriminatory it's going to be, because if we're already starting at a positive value, we're somewhere up here already. So if let's start a new graph over here. We've got a nice new graph that we're going to look at just the difficulty. So we're going to start off with this negative 3.14. So in this case, it's starting, and we're also going to think about slope too. I'm going to use both of these. So it is starting off low, but we have a very steep slope, which means it's curving super quickly and then plateauing. And I get this information both. We have big slope, but it's still starting at 0. Now, if we have something that doesn't have a lot of difficulty, so let's say with this one, it also doesn't have a lot of a steep slope here. So if we're looking at item 3, I would expect that there might be, because this doesn't have a high slope, we're probably already starting somewhere here. So we're not actually starting at 0 ability anymore. We're starting a little bit above it, but we're not going very high. It's a pretty shallow slope. We do eventually get to a plateau, but because our slope is not as steep, we aren't getting there as fast. And potentially with that difficulty, it's probably moderate. This one right here, that is not difficult at all. So I would expect that's starting somewhere way up here. So essentially, we can look at this table and see how the item is distinguishing amongst the factors, or distinguishing amongst ability levels. We don't really need to pay attention too much to these. This is just testing, are people responding in different ways? They should if we're capturing students across different ability levels. So I'm not expecting these values to be very insignificant. If these were 0 and we had no slope, then these might be insignificant. So these two go for testing slope. These two go for testing difficulty. We do see some not significant ones here when we're seeing values closer to 0. But there's not a one-to-one in terms of this because there are some other statistics that are going on here. So I mainly want you to focus on difficulty and slope values and thinking about what that means for the shape. And then the final thing that I want to cover here is that eigenvalue. Ignore the polychloric correlation matrix. We're not going to think about that for now. The main thing we want to know is, we know if they're using eigenvalues, they are testing how many factors they have. They told us that this should be a single factor measure. So when they have one factor, how well do all of these group together? They're getting a 5 right here, which is quite high, especially when we look at other numbers. It looks like here they actually forgot a period, because that would be a huge number, but I have a feeling that's 0.17. We go from 5 to 0.87. That is a pretty big jump, which tells me that one factor is reasonably explaining the behavior of a person's responses across all items. Whatever this measure is measuring, it's measuring one thing. There's minor things that are coming up as we build more and more factors, but they're not really helpful at explaining too much more, because they're not getting above a 2 or so in terms of value. And depending on what you're measuring and how many items you have, you might have different thresholds for this number, and the researchers should tell you in their methods what their threshold is. But in general, you want a big number above 1, ideally more than 1 by quite a lot, to indicate this factor structure tells us important information on how a person responds to the items, thinking about what construct or what skill is contributing to what a student or participant is doing. And in this case, whatever skill they're trying to assess here is getting captured across all of these items, and there isn't another skill that separates out some of these items as measuring something else. So that is primarily what they're showing us with the eigenvalues. Now, if we go to the second table, the other table that they give is the actual item response functions, which is essentially the probability of a person getting that answer right based on their skill level. And again, they're going from a -4, 0 being average, 4 being well above average. The key thing you want to look here is, where is 0.00 happening and where is 0.99 happening? Because that tells you, when we're thinking about that curve, let me draw that real quick. Oh, that was really bad. Ignore my not straight lines. But the zeros and the 0.99s tell us where those plateaus are. So for this first one, that one had the super steep slope. We're hanging out fairly flat. We get super steep real quick because we have to account for a change from 0.12 to 0.84 in terms of the likelihood you're going to get this answer right. And by the time, essentially, you get to average, we've plateaued, and you're probably going to get this right. So let me put some markers here where we got 1, 0, and 0.5, roughly. So if we are thinking about those, and this is our probability scale, we have our ability scale down here. Remember, item 1 had a really steep slope, and it had a really low intercept that was technically negative numbers. We're starting at 0 because that's where our probability starts here. But in general, we're getting this really steep S-curve right here, where it is pretty good, I guess, at discriminating between maybe these two values here, the -2 and -1, because we have a change in value that's pretty significant. But once we get to 0 average ability, it's not telling us anything about these students up here. So a good item for that student pool in the like slightly less to average skill level, not useful for the upper or lower ranges. Now, one thing you might notice in this scale, especially if you start looking at this column for 1 and above, particularly when you get to 3 or 4, it's not super good at discriminating between above average and really above average skills. Like, as you get to columns 3 and 4, all of those are pretty much 0.999, so you're very likely to get this correct by the time, for the most part, you have at least above average-ish. And even when you get to the 1, those are still really high, 0.8, 0.84, 0.88. That's a really high probability of getting an answer right. And this is one of the things they do discuss in this article, is that they have pretty decent discrimination for this range of ability level, so also not great for super bad, because those are just zeros. And we get a little bit of discrimination here. So it really is just getting this group of mildly below average to a little bit above average in terms of math performance. So it's not, I would say, the most discriminatory measure for various reasons. And it looks like they have some issues with uh, either difficulty on the low end or just in general things being too easy and it's not difficult enough to capture what's happening on the high end. So sometimes researchers will give us these tables, sometimes they won't. I appreciated this article in giving us this table and being honest about their measure, because it lets us know that this might not be the best at capturing skill level above a certain point. That's good to know when we interpret their results. So why did they show us all of those tables? I kind of just hinted at why they did, but they designed their measure rather than using an already validated one. So they needed to show us that their measure was working to be able to discriminate against across students' abilities, because that's what they were trying to show, was how different kinds of math homework help students or affect students' test scores. So anytime you make an assessment, you need to provide that information about how well it works. In part, it's a giving your reader the ability to trust you in terms of the measures that you're using because you made it. They can't go check your work if it isn't already a validated study. So they need to, or a validated measure, so they need to know that what you designed was good quality. And then showing their IRT information specifically, because this was looking at a math skill in particular, shows us how well we can trust their data in terms of how we can interpret their data. So we might have a little bit of wariness about thinking about the ways kinds of math homework impact students who are of above average ability. And that may or may not be something we're concerned about. We might want to know how it's helping these under average to average students. Depends on what you're studying. So in this case, the IRT is really showing us how reliable and also how valid their measure is, because it's letting us see, is it capturing one factor? Is it able to discriminate and distinguish students by ability level? So we really want to pay attention to that discrimination, so that slope and the difficulty. We know that the data getting produced by students isn't random, and it's their skill involved in answering correctly. That's our assumption of a well-designed measure. If the IRT information tells us otherwise, then that affects how we interpret it. And then those eigenvalues are particularly important for the validity if we're actually measuring the constructs we want to. In that article, they also tell us that they did important additional validity processes besides using IRT to test their measure. They do talk about that they had 3 6th grade teachers also help them make that assessment. That is using expertise as a proxy for good assessment design. There are some assumptions in that. Maybe, I don't know how well these 6th grade teachers think about assessment design. I'm trusting that they have good design, but I don't actually know. So expert opinion can be helpful. You shouldn't be relying on it as your only measure for validity. And so the fact that they did have eigenvalues to be an additional measure gives me some peace that they were at least measuring that skill. I do know that. Now, the last thing I want to go over is walking through a correlation table. This table also comes from that study because we're going to see these fairly often, and they look different than those regression tables. So I want to walk through how we interpret these. So in general, what you will see is a title of the table that tells you what they're doing. Sometimes it's more or less important, but we do know they're using correlations. We then look over here at all the different words because that tells us what variables they are doing the correlations with. And you'll notice they're numbered here, 1 through 8. That's important because if you see over here in the columns, we go 1 through 8. So rather than putting the actual words here and making it a kind of hard to read column, they use the numbers as number 1 up here is gender up here. And then we essentially look at how each of these fall in terms of correlating gender with other variables. You'll notice there are dashes here. Sometimes there are dashes, sometimes they're just 1, because if you're going to correlate gender with gender, you should have a one-to-one correlation because it's the exact same data. Not really useful for us, so in this case they did dashes. We don't really want to pay attention to it. However, we want to see what's happening across other variables. So, for example, if we want to see what's happening here at that first number, we know it's mathematics self-efficacy correlated with gender. And in this case, there's not a correlation. It's 0.06. That's pretty much almost zero. Well, the next one is basically zero, but we're thinking about correlations in a range from -1 to 1. And that's because the sign is important. The sign tells us the direction of the relationship. So let's see. Technically, all of the ones that are pretty significant, and again, they do tell us indicators of significance here. We do have a negative one that is significant. We have this 0.09 here. Again, not a super strong correlation, given that if our scale is -1 to 1, it's still barely away from 0. But apparently, the amount of time you study is slightly negatively correlated with gender. And luckily for this one, they do tell us how they coded gender. So the more time that you studied, you were more likely to be coded as female than male, is what it's showing. Because we can, they don't give us this in this paper, but if we wanted to, we could look at this. If, say, gender is what we were predicting, where 2 is male, 1 is female, and this is time studying, that is an M. The more time you studied, because we have a negative value here, and a negative, essentially there is this kind of relation. That is much stronger than what this actual number is. In fact, I might actually try to replicate that more. Maybe it's like there's a very small slope happening here because that is only 0.9. It's not super strong. But if you were coded as female versus male, it was more likely that you were studying more. If you were studying more, it was more likely you were female or versus being male. So that is what this relationship is talking about. Thankfully, I did the highlighting on here for my PDF. That's why those are highlighted. They're not highlighted in the raw PDF, but they do give us the asterisks to tell us how strong the significance is. And we've got 1 for under 0.05, but still above 0.01. Getting under 0.01, but still above 0.001, and then under 0.001. So we really, we want to pay attention to all of these, but really we want to think about these 2 and 3 asterisks. So when we look at this table, we can go look at what are the strongest correlations happening in this table. And the strength of the significance is not a one-to-one with how strong the correlation is, because obviously we can see that this has 3 asterisks, so it's pretty significant, but it's only 0.36, and its neighbor right above it is almost 0.7. So those are 2 different values. But essentially what these are showing is that there is a definite relationship between, it looks like, prior knowledge, so your pre-test mathematics achievement that they did, and our column is mathematics self-efficacy. So the more confident you feel you can do math, the better you probably initially did to begin with, the better you did apparently after and the post-test, and it seems like parents' education level has some relationship with mathematics self-efficacy. So a correlation table we can use to look at the relationships across a lot of different variables, and you are essentially able to see how the variables relate in any combination you can get of 2 variables. So we can look at parents' education level and prior mathematic or the mathematic post-test, where there's a correlation here. Looking at column 7 and row 8 here. So correlation tables are super handy to see what relationships are happening in the data. Now, correlations don't mean causation. There is a relationship happening here, and we can hypothesize some potential causes of why a parent's education level is this impactful on their student. It's got 3 significant correlations that are really strong, or pretty strong. They're about 0.3, 0.4, but they're pretty significant. There are things we could hypothesize about that, but because they did not test those or capture in this study more detailed information about what was happening at home in terms of students' interacting with their parents. There's a lot that could be happening to cause this. We don't know, but we do know that it is an impactful factor on students' scores, particularly for their pretest, their post-test, and how confident they feel about math self-efficacy. So correlation tables have a lot of information in them, and it takes a little bit of time to piece together, okay, what is the relationship? What are the two variables I'm comparing? How big is the value? Is it negative? Is it positive? Where are these significant values? And for variables that aren't potentially continuous, so like gender was binary coded, what is the coding? Because that tells me how to interpret a negative value or a positive value. So it is important to look at what they give us for a key, and then also what are the variables that they're telling us. So it takes some time to look through a correlation table, but once you piece together what relationships you want to pay attention to, particularly which ones are significant, or if there was a relationship they hypothesized as the researchers that ended up coming out non-significant, we might want to pay attention to that too. And we could look at that real quick too. Let's see. Oh, they do have mathematics time study, so how long students were studying. So when we look at item 5, we can look at it across the row. We can also look at it the other way because of the shape. But it's not, we get a little bit of that gender one that we did, but it's not affected by your self-efficacy or your homework purpose, so the kind of homework you were given, or the amount of homework you did. And then we can also look at 5 as the column here, where now we're looking at it didn't really affect how well you did on your test, pre-test, or your post-test, or your parents' education level. So mathematic time you spent doing homework for math wasn't really impacted by much at all. There was only one small significance. So a lot is going on. And depending on what the research questions are, what your questions are going into the study, which may be different from the researcher's questions, you can get a lot of information out of the correlation table.